a curious discovery of Poisson. Now recall that our jury verdict probabilities were given in terms of the binomial distribution. And there was this question about how one computes these probabilities. You should bear in mind the time. It was early in the 19th century. And to compute a binomial probability by hand was going to be moderately unpleasant. So there was a computational question. Of course, these questions are moot today because even the simplest of our handheld devices can chew up calculations like this in a trice. But in the 19th century, computation was actually really a serious question. Poisson went ahead and analyzed his expressions using the law of errors, what we today call the central limit theorem. And this will be our concluding tableau. But along the way, he noted, as a curiosity, a curious little approximation to the binomial, which could in principle be used to simplify the calculation of these binomial probabilities. This was going to have unexpected and subtle effects. So let's start with a setting. Remember, this is about a jury model, and P represented the probability that a juror made an error. Naturally, we hope that P is a small number. In the context of coin tossing, then we are thinking about tossing a coin which is very heavily weighted towards failure. A failure here means a correct decision, right? Slightly twisted language, I know, but there it is. So if P is small, then we'll require very many tosses of this coin before one sees a success, a head, an error. This is the province of rare events. So naturally, we're now thinking about a setting where P is a small positive number and N is sufficiently large. In this domain, we recall the expected number of successes for the binomial was N times P, the number of trials times the success probability. If P is small and N is large, then N times P could be a moderate number. Let us call that by the Greek letter lambda. So the setting is the following. I want to evaluate binomial probabilities where P is small, N is large, and the product N times P, or lambda, is a moderate number for varying successes. So let us fix K, okay? 0, 1, 2, 3, 4, and so on. Fix that and think of a large N and a small p. Now the binomial probabilities have got two parts to the expression. One, a binomial coefficient, and then a power of 1 minus p. Let's take them individually. First, the binomial coefficient times a power of p. Now, what is the binomial coefficient? Well, n choose k is n to the k falling over k factorial, or writing it out, n times n minus 1 times n minus 2 through n minus k plus 1. In other words, start at n and go through k terms, each one less than the previous term, the whole divided by k factorial, and then multiplied by p to the power k. Each of the terms in the numerator of the fraction is very close to n. Remember, n is a big number, k is some fixed number. So when you take away a small fixed number from a large number, you're still going to get essentially the large number. Each of those terms is essentially n. Let's reinforce it by pulling out a factor n from each of the terms in the product in the numerator. So you have n. Then if you pull out n from n minus 1, you get n times 1 minus 1 over n. Then you pull out n from n minus 2, you get n times 1 minus 2 over n. And so on down, you pull out n from the last term, you get n times 1 minus k minus 1 over n. So how many n's have we pulled out? Well, there are a total of k n's in the numerator, k terms in the numerator, and each of them has contributed one term n, and so we get n to the power k. Combine that with p to the power k and write it as simply n times p to the power k, and now we've got an expression. N times p, the mean of the expected value of the binomial to the power k, over k factorial, times a bunch of correction terms in round brackets. But here's the point. Each of the correction terms differs from 1 by a very small amount in a reciprocal of n. And remember, n is large. And therefore, each of those k terms is very close to 1. You multiply them out, you get something else which is very close to 1. And since n times p we are calling lambda, the entire product evolves into something like lambda to the power k over k factorial. So here now, the entire binomial coefficient is simplified into a much simpler form. A power of lambda divided by k factorial. We're halfway there. Now let's take a look at what remains in the expression for the binomial probability, 1 minus p to the power n minus k. The rule of exponents tells us that when you have x to the power a plus b, we can write it as x to the power a times x to the power b. Identify x with 1 minus p, a with n, and b with minus k, and we've got a rule of products. In the first term on the right, 1 minus p to the power n, recall that p is simply lambda divided by n, or lambda is n times p. And therefore, rewrite it as 1 minus lambda over n to the power n times 1 minus p to the power minus k. Now, the second of the two terms, remember, p is very tiny. So 1 minus p is very close to 1. And you're taking a number very close to 1 and taking a power of it, you're going to get something very close to 1. 1 minus p to the power minus k is approximately 1 for small p. What about the first term? Oh, there might be a faint atavistic tug in your memory banks, perhaps from your first calculus class or your pre-calculus class. 1 minus lambda over n to the power n. Remember, lambda is a moderate number. N is a large number. This expression is an approximation for e to the power minus lambda. In fact, we could use this as a definition of the exponential function. And therefore, we get e to the power minus lambda times 1 approximately, or simply e to the power minus lambda. Everything is simplified gloriously. The binomial probability of k successes in n trials with a success probability of p is approximately given by lambda to the power k over k factorial times a to the power minus lambda. A new student, a neophyte, might well be pardoned for being skeptical about this strange algebraic maneuver. So what have we accomplished? Well, I've got a messy thing, and I replaced it by some other messy thing. But something important has been accomplished. Take a look anew at the binomial probability on the left. It, for a given k, is determined by two parameters, n and p, and each of the terms is not easy to compute, especially by hand. N choose k is complicated. It takes effort. And you have various powers of p and 1 minus p. On the right, we have a single parameter, lambda. Our entire expression is approximately determined by a single parameter. And this is going to have deep consequences. We should promptly rush in and put in some nomenclature, some terminology to capture this. On the right, I've got an atomic mass attached to k, a probability that some suitably designed chance experiment takes value k. It is completely determined by one real parameter, a positive number lambda, which is fixed once the parameters n and p are known. Let's call this the Poisson probability, PO for Poisson, of k emerging in a chance experiment with a hidden parameter lambda. Now, this looks all very esoteric, to be sure. But as a first question, you say, well, maybe Poisson had to do something with this. But surely today we have access to computing devices. Why do we care? We can just throw the binomial probabilities into the machine and out comes an answer. The answer is going to be nuanced and at least twofold. The first part of it is simply the following realization. An expression like this already gives us a lot of information that we were not privy to earlier. What this tells us is that a variety of binomial expressions, a variety of binomial experiments with differing n's and p's will give rise to similar probabilities as long as the product n times p is a constant. So a whole slew of binomial expressions all give rise to similar chance outcomes. That is an important realization. The second question that might arise at this point is, well, we've waved our hands around and done these algebraic approximations. How good are they? We could approach this in a couple of ways. One is we could try to make a formal limit theorem out of this and try to provide explicit expressions for the error we make in such an approximation. And that can be done, but we won't bother. We'll simply appeal to your numerical evidence to see that this actually gives us convincing results. So here is a test of the quality of the approximation of Poisson. Start with the binomial probabilities corresponding to two parameters n and p. Let the number of successes k run from 0 through, say, 4. And allow n to range over suitably large numbers. In this case, I picked 20, 60, and 100 as my large numbers. Allow p to range from 0.15, 0.05, and 0.03, 15%, 5%, and 3% in the three cases, respectively. The number is so chosen that n times p is a fixed value 3. This is my lambda. So in each of the three cases, n is 20, p is 0.15. n is 60, p is 0.05. n is 100, and p is 0.03. We have n times p equal to lambda equal to 3. So n is large, p is small, lambda is a moderate number. The Poisson probabilities that we've called PO of k, parameterized by lambda, are given by lambda to the k over k factorial times e to the minus lambda, and here's a table of values. And even a cursory examination shows that the approximations are getting quite remarkably good, even for these relatively small values of n. We could, at this point, create a test of a hypothesis, but we will not bother. At a high level, all we will need is to say, if we are in the province of rare events, where the coin toss has got a small probability of success, p, then if there are enough trials, if the coin is tossed enough times, then the binomial probabilities are approximately governed by Poisson probabilities. The approximation is quite remarkably good, even for small values of n.